All right, for Unit 10, we're going to take a look at some exponential functions. We're going to start working with these. Now, when we talk about exponential functions, we're talking about a function where x is an exponent. So that's what makes it exponential. And so the input value, the numbers that we're changing in the function are the exponents. The base will stay the same. There are two basic types of exponential functions. There's exponential growth and exponential decay. So for exponential growth, the b value, the base, is greater than 1. And for exponential decay, the b value, the base of the power, is a number between 0 and 1. So some sort of fraction or decimal that's less than 1, but not a negative number. These are all positive bases. So let's take a look at first exponential growth functions, where the base of our function is a number greater than 1. We're going to look at f of x equals 2 to the x power as our example. So let's graph this by just making a t-chart. And I'm going to go ahead and put in 5 numbers like this. So if I do 2, or negative 2, 2 to the negative 2 power, well, that's 1 over 2 squared, which is 1/4. So a negative exponent flips the power into the denominator, and so we get 1 over 2 squared, which is 1/4. So negative 2, we have a point here at 1/4, which is about here, approximately. Negative 1, well, that's 2 to the negative 1, which is 1 over 2. So at negative 1, we're at 1/2. For 0, anything to the 0 power is 1. So 0, 1. Now that's always going to be a point, 0, 1, unless you have addition or subtraction after the power. For 1, 2 to the first power is 2. And for 2, 2 to the second power is 4. So notice how the positive and negative inputs sort of give you the reciprocals. So we have 4 and 1/4, we have 2 and 1/2, and then 1 in the middle. So our graph increases to the right and decreases to the left. Now, if we're talking about this in general terms, the domain here of any exponential growth function is going to be all real numbers, because I can put any number in for x, negative or positive, and I'll get an input, or I'll get an output for y. So our domain here is all real numbers. X can be any number from negative to positive infinity. The range of our graph, now this is what's more interesting, I think. You can see the graph does go up forever. It's going to continue rising as we go forward in x. It's going to keep going up in y faster and faster. So for any number x, the y value is going to be much larger. Now, on the negative side, we're going to get closer and closer to 0, but we're never going to cross into the negatives because of the way exponents work. A negative exponent just gives me a smaller and smaller fraction. It's not going to be a negative number. So the range here is just all values of y that are greater than 0. And that's because we have what's called an asymptote at 0. There's a line here at 0 that our graph is never going to cross. The asymptote here is at y equals 0. Okay, let's take a look at exponential decay. Based on the words growth and decay, you might have some idea of what this is going to look like, but we'll make a little t-chart, same as before. I like to do 5 numbers because it really gives a better sense of what the picture looks like. Now we have 0.5. This is 1/2. So depending on how you feel about fractions and decimals, it might be easier to think of this as fraction 1/2, especially because the negative exponents will flip it. But you could just as easily use a calculator with 0.5. It would work just fine. So for negative 2, that's 1/2 to the negative 2. remember that's going to flip the fraction, and it's going to be 2 over 1 to the second power, which is 4. So I have a point at -2, 4. And like I said, you could use a calculator and do 0.5 to the -2 power, and you still get 4. So you can use a calculator, just use the decimal as well, that's fine. For -1 to the, or so for 1/2 to the -1 power, that just flips it, we get 2 over 1 to the first power. For 0, anything to the 0 power is 1. For 1, that's 1/2 to the first power, so that's going to be 1/2, or 0.5. And then for 2, it's 1/2 squared. 1/2 times 1/2 is 1/4. So we have a point at 2 1/4. So because we used 1/2, which is just the reciprocal of our base for the first one, we just have an kind of inverted chart. We have the same numbers just on opposite ends. So we go down towards 0 from left to right instead of up away from it. Okay, so we have similar observations here for the properties of this graph. The domain here is still going to be all real numbers. I can put any number in for the exponent here, and it will give me an output. The range is, again, very similar, greater than y, and the asymptote is the same, y equals 0, because we're approaching 0, but we'll never cross it. The main difference here between exponential growth and decay is that since the base is either greater than 1 for growth or less than 1 for decay, our growth functions go up to the right because the output is growing as x increases, and the decay functions go down to the right because our output is decreasing as our input increases. So let's try graphing some functions here. F of x equals 5 to the x power. Now, if you're graphing these quick and you kind of understand how these work, it's really okay to do 3 points. I like to do 5, just to get a better idea of what the graph looks like, but you don't always have space for this. So -1 gives us 1 over 5. So we have a point at -1, 1/5, we'll call it that. 0 is going to give us 1, and 1 is going to give us 5. 5 to the first power is 1. And you can see if I put a 2 in there, I'd get 25, and I don't have space on this graph. I could put -2 and get 1/25, but that's essentially 0 just because of how big of a graph we have. So this is good enough to get an idea of what this graph looks like. And it is an exponential growth function because it's going up to the right. We can see that the base is bigger than 1, so that's good. 0.25, that's 1/4 if you're a fraction user. Again, we could just do 3 numbers. -1, 1/4 to the -1 power. That's going to flip it to 4 over 1. So -1, 4. 0 is going to be 1 again. And 1 gives us 1/4, or 0.25. And again, you can see this graph like this, exponential decay. And you can see how as we increase that x value, 2 would give us 1/16, 3 would give us 1/64, closer and closer to 0 without ever touching it. Now we can also translate these graphs a little bit. So if we change our equation a little bit, if we add or subtract numbers in the exponent, or add or subtract numbers afterwards, that can have an effect on the shape of the graph. So h here, the number added or subtracted to the exponent, that gives us a horizontal translation. If it's a plus, x plus a number, it moves to the right. If it's, or if h is positive, we move to the right. If h is negative, we move to the left. And then k is our vertical translation. It goes up if it's positive and down if it's negative. Just, when in doubt, you can make a t-chart. That's what I usually do just to be sure anyway. So let's try this one. Maybe I'll put a middle column here in my chart. We've got space for it. That way, if I have to show some work, then I'll be able to. So let's go ahead and do our 5, -2, -1, 0, 1, and 2. That'll give us a good idea of the picture. So for -2, that's going to be 2 to the -2 plus 3. That's just 2 to the first power. So that's a 2. For -1, that's 2 to the -1 plus 3, which is just 2 squared. That's 4. 0 is going to be, well, it's not going to be 1. See, you can't always assume. 2 to the 0 plus 3 is 2 cubed. 2 times 2 times 2 is 8. 1, 2 to the 1 plus 3, well, that gives me 2 to the 4th, which is 16. And you can see the pattern here, 2, 4, 8, 16. We're going to get 32 here for 2 to the 5th power. Remember, just like with linear equations, you will see a pattern show up if you put your numbers in order. Now, this isn't a linear pattern. The number is multiplied instead of added, but we do see a pattern. So -2, 2 gives us right here. -1, 4. 0, 8, and that's about as much as I can do. I can't fit 16 and 32 on here. But notice we didn't really get to see the back half of our graph. So I'm going to go ahead and do a couple more numbers here. Let's do -3 and -4. I'd like to see the whole picture. I can't assume where this left half is going. So this one was -3 gives us 2 to the -3 plus 3. That's going to be 2 to the 0. So that's a 1. And -4 plus 3 is -1. So that's 1/2. That feels a little better. So -3, 1, -4, 1/2. Now I can see what's happening. Now we're going to approach 0 here. So this is what my graph looks like. Exponential growth. Probably it would go a little faster down, but as long as it's close. Okay, so you can see here, hopefully, that when we didn't have a translation, it kind of was centered on the y-axis. But here's the y-axis on this problem. So since we had a +3, we moved left 3 spaces. Right, so where I would have been centered on the y-axis with my 0, 1 point, which normally is right here, now it's right here. I moved it left 3 spaces. So we had a positive, well, I guess it was a negative because it would have been x minus -3 up here. So h technically is a negative number there. It's a -3, but we moved left 3. So if it says plus, you're going to move to the left because that's what we're subtracting, that h value. Anyway, when in doubt, make a t-chart rather than try to wrap your head around like what the graph should look like and then move it. Just make a little t-chart and then you can see what the graph is going to be doing. Let's try one more. Okay, we'll do our 5. Maybe I want a middle column on this one as well. Always nice if I have a little work to do. So this is 1/2 to the x plus 2. Okay, so for -2, 1/2 to the negative 2 is 2 over 1 to the second. So you can flip it ahead of time, make it a little easier on you. I'll just fill out this middle column first. Negative 1 does the same thing, flips it to 2 over 1, or 2 to the first power, plus 2. 0, we get 1/2 to the 0 plus 2. For 1, that's just 1/2 plus 2. And 2 gives us 1/4. 1/2 squared is 1/4 plus 2. All right, so 2 times 2 is 4, plus 2 is 6. 2 plus 2 is 4. We've got 1 plus 2 is 3. 1/2 plus 2 is 2.5. 1/4 plus 2 is 2 1/4. A little harder to see the pattern this time. We decreased by an exponentially smaller amount each time. We decreased by 2, then by 1, then by 1/2, then by 1/4. So the next one would be by 1/8, and so on. So there is a pattern, it's just not a linear pattern. Now for the graph, we got -2, 6. Well, I can't put that on the graph, it's somewhere up here. -1, 4, 0, 3, 1, 2.5, 2, 2 1/4. This is interesting. See what's happening here? I'm going down, but I'm not approaching 0. I'm approaching 2. So I moved from my asymptote being here, moved it up 2 spaces to here. And that's because of this plus 2 right there. So that's going to change where your asymptote is. It's going to move the whole graph up or down if it was negative, but we moved it vertically 2 spaces, and now we have a new asymptote. And see, the numbers here start to approach 2, but they're never going to get closer to, they're never going to equal 2. The next one will be 2 1/8, 2 1/16, 2 1/64. Going to keep getting closer and closer to 2, but never touch it. Okay, so that's how adding or subtracting numbers in different parts of the function can affect your graph. But essentially, they're all going to be the same shape, where in one direction you're going to go up forever, and in the other direction you're going to approach some number, usually 0, but sometimes it can change if you're adding or subtracting at the end. Okay, but when in doubt, just make a t-chart, throw in some numbers. If you don't have enough to see the whole picture, add a couple more numbers, and then you can get a good graph on there.